So far, we have dealt with procedural programming, which involves writing a code that is sequentially executed. We also studied integers, floats, strings, list, tuple, and dictionary. Now, those are called objects in Python. An object is the building block in Python's object-oriented language. Each object in Python has an associated data type. For example, integer objects have int type, string objects have str type, dictionary objects have dict type, and so on. All objects have types, but in object-oriented programming, data types are referred to as classes. If you assign an integer value of 1 to variable x and you print the type of x, you will see that the result is referred to as class integer. This means that the variable x belongs to the integer data type or integer class. Printing the type of other data types reveals to which class an object belongs to, as in the case of the string and the dictionary in this code example. Now, Python provides you with essential data types such as integers, floats, strings, list, tuples, and so on. However, what if you want to create your own custom class or a custom data type? This is where object-oriented programming comes in. In real applications, you do not only deal with data such as integer number, or float number, or texts with strings, but you also deal with different data types such as audio, images, and videos, or maybe a combination of everything depending on your application. You could be writing a program to manipulate photos just like a photo editor program, or a program to manipulate PDF files, or you could be building a video-based surveillance system which detects certain events. A single photo, audio, PDF file, and a video are objects that belong to a certain class or data type. Instead of having a class only defined by Python, you can build a class that is defined by you. There are many benefits of using classes in Python. They will be discussed in this section and also in future courses. We define a class in a similar way to what we do in functions, but we use class instead of def to denote the definition of a class. The name of this class is my class. The second difference between a class and a function is the naming scheme. Naming a function follows the snake case, which involves using an underscore between words in conjunction with using lowercase letters. On the other hand, naming a class follows the camel case scheme, which avoids using an underscore between words while keeping the first letter in each word as uppercase. This is just a used convention by the community, not a rule of thumb. Having seen the syntax of a class, we need to understand certain terminologies that are associated with classes. Those terminologies are object, type, class, instance, and methods. You already heard about them in the previous sections of this course, but we will define them now. The first term is object. Objects are Python's abstraction of data, so almost everything in Python is an object. 2.5 float number is an object, a list of integers 1, 2, and 3 is also an object. A function is an object, a tuple is an object, and so on. Not only that, a combination of all of them is also called an object. When you have, for example, x equals 2, you are basically assigning an object 2 with integer data type to a variable called x. A data type has specified operations that the object support, and also provides a limited supported values which the object can hold. For example, if you have two variables x and y each with integer numbers, the integer object allows you to do mathematical operations between integers, as in this code example. The integer object allows you to add integer to a float number, but the result will be a float, not integer. However, the integer object in Python does not allow you to add an integer to a string. If your string is numerical, you can change the type of string to integer using the int function. Note that you can always check the type of an object using the type function. A class is a process that Python provides you to create a custom user-defined data types. The concept of class is similar to the concept of type. To avoid confusion, we will use the word type when we refer to types already provided by Python, such as strings, floats, integers, dictionaries, tuples, lists, etc. However, we will refer to types as classes when we are talking about custom user-defined types or custom user-defined classes. Instance is an individual object that belongs to a certain class. For example, string 1 and string 2 are two instances of the string class, but each of which has a unique value. Instances are synonymous to objects, so you can say string 1 is an instance of the type string, or you can say string 1 is a string object. Now, let us define a class called myClass, which has no input arguments. The body of this class is the keyword pass. Pass in Python is used when an expression is syntactically required, but you do not want any command or code to execute. Therefore, it is just an executed dummy line of code that does nothing. We are doing this just to illustrate an example, so this class does nothing. Then, we are instantiating an object of class myClass and assigning this resulting instance to a variable called myClassInstance. Therefore, the instance myClassInstance is an object with type myClass, as you can see in the output of the code. To illustrate this furthermore, we will use the built-in string class in Python. In previous lessons, we learned how to convert an integer to string using the str function. What we have done here is that we instantiated an object of class string with string value 10, and assign this instance to a variable called x. So in a nutshell, objects are abstraction of data in Python, and instances are objects which are obtained through a Python built-in or user-defined class mechanism. We previously checked how the syntax of functions and the benefits of using them. We mentioned that the main purpose of functions is to perform certain action that can be applied to input arguments to return certain values according to the action performed by the body of the function. Also, we saw that functions can also be used to not return any values. However, this was not the only way we have performed actions on objects in this course. Do you remember how we added elements to a list using the append function? To append more elements to a list, we followed this syntax. It will be the old list followed by the dot, and the append of the new element. Functions written in this way are not called functions, they are called methods. In this case, append is a method that performs the action of adding a new element to an existing list. So what are methods, and how do they work, and how to build a custom user-defined method? This is what we will study. Let us look at another example. String objects have a method called replace, which is used to replace certain specified characters with a new one. This is the syntax of the replace method. This will replace an old value with a new value. We have a string value assigned to variable x. You can replace part of the string value, such as the word banana, with apple string using the replace method. We are also printing the value of x before and after replacing the string values, as you can see in the output of the code. In a nutshell, each class in Python has its own methods that only applies to it and not on other data types. The methods we have seen are also built-in ones provided by Python. Now, we will study how to create custom user-defined methods. We will modify our myClass class to have more functionality as its body was only pass statement which performed nothing. Creating a method inside a class is almost done in a similar way as functions using the def statement. The methods function will be the body of the class definition. In this code example, the myClass class has a method function called printBody. The printBody method is supposed to print this string value when applied on an instance. After class definition, we will instantiate the class to a variable called myInstance. Now, let us apply the first method on our instance myInstance in a similar way we have applied the append method on a list object. We expect that the string value, this is the body of the applied method, is printed when printBody method is applied on myInstance. However, we are receiving an error mentioning that printBody method takes 0 positional arguments but 1 was given. It is strange that Python is observing that we are inputting an argument to our method although we did not specify any input argument whatsoever. What is this argument that is detected by Python? Why is it even there? Where is it hidden? Let us look back at the append example. In this case, we have a variable called numbers that belongs to the list class. Then we are taking this list object and applying the append method on it to append the integer value 5. Now, how does Python interpret this code line? It will first search for the class of the variable numbers, and it will see that it is a list class. Next, it will search within the list class for a method called append in order to apply it on the list object numbers. In this case, Python automatically passes 2 input arguments to append method. The value 5 you set as an input argument to the append method, and the object that the method will be applied on which is the numbers variable. Although we have set a single input argument to the append method, still, Python automatically adds the object to the method as input argument as well. Knowing this, how can we resolve the error that we have seen earlier regarding the additional input argument? We will be using the same code we created before, but we will add one keyword as an input argument to the methods function, and that is the self keyword. Here the self keyword refers to the object we are applying the method on, so the self keyword here represents the myInstance variable. Notice that there is no input argument in the printBody method definition inside the myClass class except for the self keyword. Therefore, the printBody method only sees a single input argument which is the myInstance variable. The self keyword must always be used when creating methods as their own input arguments. Now that we know the terminologies associated with classes and the syntax of a class, we need to look at the bigger picture. We saw that within classes, we developed functions called methods. Then the question is, why do we need to create a class if the core of it is just functions? Isn't using functions enough? The answer is no, because classes produce objects which normal functions cannot. Let us look at this scenario. Suppose you are building an application whereby the user can enter macronutrients of a fruit per 100 grams of weight, and the application prints the total calories of the fruit itself depending on the actual weight of the fruit. Not only that, but also the user can enter the name, weight, and color of the fruit. Now suppose the user wants to enter the mentioned characteristics for apple and banana fruits. To represent each of these fruits, we need to store 2 sets of information. First is the properties that each fruit possess, such as the fat content, carb content, protein content, weight in grams, and color. The second information you need to store is the set of functionalities you want to apply on those properties provided by the user. In our case, the functionality is to return the total calories of the fruit provided. Now, how is it possible to organize the set properties and functionalities? This is done by creating an object. Objects are a collection of single or multiple variables and/or functions. Now, each fruit has its own properties. Apples have 0.2 grams fat, 14 grams of carbs, 2.4 grams of fiber, 0.3 grams of protein. It also has red color and 120 grams of weight as an example. For the second fruit, that is banana, it has 0.3 grams fat, 23 grams of carbs, 2.6 grams of fiber, 1.1 grams of protein. It also has yellow color and 132 grams of weight as an example. Therefore, the set of properties and functionality on the left are represented as an apple object, and the one on the right is represented as a banana object. The variables within an object are called either instance variables or attributes, and the functions within objects are called methods. Therefore, the variables name, fat, carb, fiber, protein, color, and weight are attributes, and the calories content function is called a method. Although the apple and banana objects share the same properties, each fruit has its own attribute values. Now, how do we systematically create different objects such as the apple object and the banana object? How do we create a set of attributes and methods that the objects can fill with values? This is done so by defining a class. A class is a blueprint or an empty template by which you can fill an object with attribute values and perform certain action based on defined methods. As you can see, the class has the same attributes and methods shown in the apple and banana objects, except the attribute in the class are empty and are not defined. This is because this class blueprint will be used to instantiate an object with values for those attributes: name, fat, carb, fiber, protein, weight, and color. When defining a class, it must have a name, so we will call it fruit. Now, we need to know how to create attributes and methods in a class definition. Creating a method for a class is done by defining a function inside a class, as we have done in the print body function, in the myClass class definition. Furthermore, there are two techniques to create attributes for a class. You can use the direct technique or by using a constructor. Let us see how do they work. First, we will build up an empty fruit class and start filling it with attributes. Then we will look how to build a method inside the class and calculate the calories. To create an empty class, we just have to use the pass statement to start with. You do not need to use the pass statement when building classes, but this is just to show you how you can build one step by step, as you cannot define a class without any body. In the direct technique of creating attributes for a class, you need to follow this syntax. You will have the instance name followed by a dot. Then you will have the attribute name equals to a value. Now, we will start off by creating attributes for an apple object. First, we have the class definition using the pass keyword as the body of the class. Therefore, this class does nothing for the time being, so we will fill it with attributes. Then, we will instantiate an apple instance by calling the fruit class. As a result, apple instance variable has an empty template or blueprint of the class to play with. Next, we will fill this empty template with attributes according to the syntax we have seen before. The attributes' names are name, fat, carb, fiber, protein, color, and weight. Each attribute is associated with a specified value. Now, the attribute's values can be accessed using this syntax which we are printing in this case. Similarly, you can create a new instance for the banana fruit with the same syntax. Now, we see in the direct technique that we first need to create a class. Then we need to instantiate the class to create the instance myInstance. Next, we can create class attributes with values using this syntax. In the direct technique, creating attributes happens outside the definition of a class. Now, there is another more appropriate and common way to create class attributes. This way involves assigning attribute values when instantiating an instance. In this technique, attributes values are passed as input arguments to a class when instantiating an instance. To do this, we need to use something called a constructor when defining a class. When using a constructor to create class attributes, you do not need to define attributes outside of a class like in the direct technique. Attributes creation happens inside of a class. Constructor is a method that is automatically called when an instance is created, and it is used for initializing basic variables. There are many types of constructors in Python, but we will now look at the init constructor to initialize class attributes. The init constructor means initialize or assign values to variables. You see that there are two sets of underscores before and after the constructor's name. In Python, this is used in order to avoid conflicting with user-defined names. Now for the method's arguments, the self keyword must always be used when defining a method. Then, the passed variables arg1 to argn follow after the self keyword. The body of the init method has the same syntax as the direct technique implemented to assign values to attributes, but instead of using the instance name, we use self keyword because the self keyword represents the instantiated instance. The attributes are automatically initialized when you instantiate an object myInstance. Let us see this in a graphical analogy to better understand it. First, when you instantiate an instance with a defined class, the instance myInstance will have the same blueprint of class. Therefore, the instance will have attributes attribute 1 to attribute n. Also, myInstance will have the same methods as defined in the class. In this case, myInstance will have the init constructor as a method defined in it. Now, once you execute the class instantiation code line to create the myInstance instance, the init constructor will automatically run. The init constructor in this case takes two inputs, myInstance variable and the values passed to the class, which are val1, val2 up to val_n. What will the init constructor do is that it will take the attributes part of myInstance and assign the values passed to the class to those attributes. But now, how does the init constructor access those attributes to assign values to them? Since the attributes are part of the myInstance instance, the attributes can be accessed by the following syntax: myInstance.attribute1 for the first attribute, myInstance.attribute2 for the second attribute, and so on. Then, the init constructor will assign the passed values val1, val2 up to val_n to those attributes. However, a method inside a class does not refer to the instance by its name, which is myInstance variable in this case. This is because you first define a class, then instantiate an instance by calling the class with values. Therefore, the methods inside a class do not know the name of the instantiated instances up front. As a result, the instances will be referred to as the self keyword. This is why we use this syntax to define attributes inside the init constructor. Now, There is a naming convention by the community that the arguments' names are written as similar to the attribute name to make things easy and more readable. Next, we need to apply what we know about class and the init constructor on the fruit class example. Here in this code example, we are defining fruit class with the init constructor as a method for this class to create class attributes which are name, fat, carb, fiber, protein, color, and weight. Then, we are instantiating two instances, one for apple fruit and the second is for banana fruit. Once we instantiate those instances, the init constructor will be run automatically and values are assigned to class attributes. As you can see, each instance has similar attributes but with different initialized values. Next, we are showing printing examples of class attribute from each instance. Now that we know how to initialize class attributes, we need to build up a method to calculate the total calories content. Here, we have a normal function called calories content which calculates the calorie content using the input arguments fat, carb, fiber, protein, and weight in grams. This function cannot be used by itself in this manner inside a class definition, so we need to make two changes. We need to change the variables to accommodate the self keyword, and remove the input arguments as the instance variables are already defined in the init constructor, but still we need to include the self keyword as input argument to the method to represent the object. As you can see in this code example, we have the init constructor which assigns values to class attributes. Then, we are defining the calories content method to calculate total calories. As you see, the calories content method does not take any input arguments except for the self keyword, since all attributes that are essential to calculate total calories are already existing inside of the self keyword, which by itself represents the fruit instances. The calories content method returns the rounded number of the total calories variable. Next, we are applying the calories content method on each fruit instance to display the calorie content for each fruit. Now, this code has a slight problem that we need to adjust when instantiating each fruit instance. The fat, carb, fiber, and protein values are always fixed regardless of the fruit weight since they represent basic facts about the fruit. However, the weight attribute can change according to the real weight of the fruit. Therefore, you always have to re-instantiate your fruit instances once you need to change fruit weight. To avoid this, you can cancel the weight attribute from the init constructor and include the weight as an input argument to the calories content method. So now, let us adjust our previous code. Notice that we have done multiple changes to our code. First, we removed weight attribute from the init constructor. Then, we included the weight variable as a conventional input argument to the calories content method, and we also removed the self keyword from the weight variable as it is no longer a class attribute. Furthermore, the fruits instances are instantiated without the weight variable as it is not a class attribute. Finally, we are passing the weight values to the method when applying it on the fruit instances. Now, you can change the weight values without re-instantiating fruit instances.